Awesome. All right, you're good to go.
Great. So thank you for the invitation and thanks for coming to hear about what we're doing with quantum algorithms and quantum simulation. I've made the talk fairly informal because this is, I believe, a fairly informal event. I encourage you, please just anytime you have a question, just unmute and interrupt me or raise your hand and I'll stop. But at any time, if what I'm saying is not clear, just let me know. And so I'm not going to go into a lot of the algorithmic details. I think given the variety of backgrounds of potential computer science and physics and varying levels of quantum mechanical knowledge, I don't think it's possible for me to go too into details for everybody. But of course, if you have questions, I'm really, really happy to explain the details. But I just want to give you a flavor of what I think are some of the most interesting questions and some of the things we're tackling in my group at Rice University. And if you have additional questions after the talk, feel free to shoot me an email or whatever. So the sort of topic that I'm covering here is a particular class of quantum algorithms. These are not the only types of quantum algorithms that we work on, but they are a very powerful set of quantum algorithms that we're interested in, and many other people are interested in. And I will tell you a story about using these quantum algorithms on what I will call traditional hardware. Of course, it's very modern, sophisticated hardware. It's things like the IBM quantum computers or IonQ or Honeywell, or the many academic labs that do this. That's what I'm calling traditional hardware. But I also want to make a connection to novel hardware approaches. And I think that it is still so early in the game that novel approaches to hardware are very valuable. And I'm not alone in this, so I think Amazon just spent $100 million in the last couple of years making a new facility that's really about a new hardware approach. So they think that, it's still early enough to really pioneer something new, and in many other places. And so I think things are wide open. Maybe superconducting qubits or ion traps, the kinds of things that are pretty well established and scaling every day, scaling to bigger systems every day. Maybe those really will be the ultimate winners, but I think there's a very good chance that there's not. I also think there's a very good chance that there may be room for multiple architectures depending on the types of problems you're trying to solve. So I'll try to justify why I have these beliefs throughout this talk. And in particular, I will sort of start with these two approaches, this kind of traditional digital approach, this novel hardware that I think is interesting, and then I'll try to connect the two into why I think all that works. So just to give you a little bit about me, I'm faculty at Rice University. I'm a theoretical physicist, but I work much with experimental colleagues to actually make these ideas a reality. And so I'll show you mainly experimental results today rather than talk about the theory. I work with, there are many experimentalists here at Rice working on ultra-cold atoms, quantum technologies, and there are many external collaborators that we have. And just, I like to acknowledge the people who actually do the kind of research that I'm going to show you. This is my group. So mainly there are 5 graduate students at the moment and some undergraduates, soon to have a postdoc coming in. But we also have many external collaborators. But I think it's nice to show you at least the people who work directly with me at Rice. And there they are. They do all the real work. So thanks to them. So here are these 2 routes that I mentioned. The first route is what I call the traditional route, or maybe the digital quantum computation route. That's here on the right. You build a circuit of gates, which I think you've been doing a lot in this hackathon. And so you start with some initial state, and then you apply qubit rotations. You apply C0 gates. You apply phase gates, whatever. And the philosophy here is if you want to understand something, you write a program to understand it. You write a program to realize the type of dynamics that you're interested in if you're simulating a quantum system. Or if you're trying to solve an optimization problem, you write a set of gates that will take you to the optimum you're looking for. There's another viewpoint, and this is actually where most of my research, but certainly not all of it, sits, and that's on this analog quantum simulation. And so in this analog quantum simulation, the philosophy is closer to building what you want to understand directly. So if I want to understand, some molecule, what I will do is I will build a system that's very similar to that molecule. in the lab. And I will do it with hopefully building blocks that are flexible enough and tunable enough that it's more interesting than just working with the original system. Maybe I can tune parameters that I couldn't tune in the original system. And this is what we often call analog quantum simulation. Very often we just say quantum simulation, but for this talk, I somehow have to distinguish between this type of quantum simulation and simulating quantum systems using a digital quantum device. And so these are two approaches, both of which I'm going to talk about today. And also, like I said, at the very end, I kind of want to hint that they're not necessarily distinct approaches, but this analog quantum simulation can be combined with the ideas of these digital quantum computations into a hybrid analog digital architecture that is really using the philosophy that you're going to program what you want to understand, but using operations that you have custom built for the problem. So using in the hardware. And I think this is quite feasible and very promising. Okay, so I've just shown some fun examples here of experimental systems that we work with or our collaborators work with. So here's an Eiffel Tower built from atoms. That's the kind of precise control that people in my field of ultra-cold matter have. Here's another example of an ion trap. Each of these dots in each of these pictures is an individual ion. And then you can use these to run various types of quantum operations. Okay, so given this kind of palette of two possibilities, I'm just going to go through them in turn and talk about first the digital and then the analog quantum simulation. In both cases, this idea of a variational quantum algorithm is going to be a useful framework to harness them. So actually, before going on, maybe have you seen some variational quantum algorithms in this hackathon, or maybe some of you are using them? Anybody?
Yeah. Familiar with VQE. I don't know if anyone is working on it though.
Okay. So then I won't assume that you know anything about it. I'll just remind you of how it works when the time comes. But basically, once you grasp this idea of a variational quantum algorithm, then both the analog and digital quantum computations can be sort of combined in this framework. So what types of problems do we want to solve using quantum computers? And different people want to solve lots of different types of questions. But in my group, the two main types of questions that we try to solve are simulating materials, simulating chemistry, basically simulating things that involve quantum mechanics. And it's maybe not a surprise that that's something a quantum computer could be good for. And I don't know if this sounds exciting or boring. If you're a computer science, maybe you say I don't care about materials and chemistry, But I just want to point out that the types of materials we do not understand in physics and material science are things like this little floating block here. That's a high temperature superconductor, and it turns out nobody knows how to understand a high temperature superconductor. And the reason is because they're quantum mechanical, that the electrons in them are quantum mechanical. And simulating interacting electrons is extremely difficult, whether analytically, pen and paper, or via supercomputers. Anytime you're trying to solve interacting quantum problems with a classical computer, you're in some serious trouble. So of course, if we had high temperature superconductors, meaning room temperature superconductors, let's say, if we had room temperature superconductors, they'd have great applications, of course, something like power transmission. Maybe you could make really nice maglev trains, an MRI magnet at the hospital. You wouldn't have to cool the magnets down. So there'd be all these potential types of things you could do with it. And there are many other materials with interesting properties, maybe some where we haven't even thought of the types of properties they may have, that are out there that could be useful technologies if only we could understand and engineer these things. So those are nice specific examples. Also in chemistry, I'm not a chemist, so the best picture I have to illustrate chemistry is whatever this green bubbling thing is. So this is supposed to represent, some chemical reactions that we'd like to understand. And in the quantum computing community, there are famous examples like FeMoco, this enzyme for nitrogen fixation. If we could do that, we could make fertilizer more efficiently by an order of magnitude than we currently can industrially. Many other things. Many multi-billion-dollar a year industries rely on understanding chemical reactions, pharmaceuticals, and so on. So if we could simulate those enzymes, which you have to be able to simulate, or it seems like you have to be able to simulate the quantum behavior of the electrons to do, or if you want to understand a high temperature superconductor, and it seems like you have to simulate the behavior of those interacting quantum electrons to do, then a quantum computer would be awfully handy. And that's one big focus of our group. The other big focus of our group is solving optimization problems. And by an optimization problem, basically what I mean is you have a huge search space of combinatorially many possible solutions to some equation or to something like this, and you want to find the few solutions out of these combinatorially many possible configurations, or so solutions to equations, or just minimizing a cost function. So for example, you could ask questions like, how many ways are there to color a graph? So you have a graph and you want no two adjacent states here to be the same color. How many ways are there to do that? That's an incredibly difficult problem if you just try to enumerate all the solutions. That's actually, you know, an NP complete problem, and it's or an NP problem, and so maybe it's not even so easy for a quantum computer to solve these, but maybe they can help in some way. Other problems: how many optimal trip itineraries that take me through a set of cities is possible? Or coming a little bit to the physics perspective, what about the number of ground states of this system that I'm drawing? So when I say ground state, I mean lowest energy configuration. If I have a bunch of spins, just meaning little magnets that are attached to all the electrons in a material, they have lots of different ways they can point in. And maybe they'd like to point in opposite directions. But you see, when there's a triangle, you can't make all three of the neighbors point in opposite directions. You know, you have to frustrate one of these, and we call these frustrated magnets. In fact, the Nobel Prize in Physics this year, one of the awardees was Parisi for his remarkable work on spin glasses. And I think maybe Helmut Kotzgraber will tell you a bit more about these types of systems. But we'd like to be able to find what are these energy minima, because they're very important to the physics. And things like all-terminal reliability. So this is just, I take a graph with edges on this graph that represent links, and the question is, if I start at one node and I look at another node of this graph, is there a connected path between them? And how many connected paths there are? And is it there for every pair of nodes? Is every pair of nodes connected? These sorts of problems can be very difficult to solve. And because I think most of us, if not all of us here, are Texans, you can probably appreciate how important understanding the reliability of a graph like this is, because a graph like this is a pretty good description of something like a power network. You want to distribute power to all the houses connected by transmission lines, and you'd like to know that if there's a 1% chance of a power line failing, or a 10 to the minus 5 chance of the power line, of one power line failing, of each power line failing, what is the probability that the network actually fails, becomes unreliable, that somebody does not get service? And we would like that not to happen. So that's an important engineering problem that I was actually introduced to by a civil engineer. So we collaborate with civil engineers, with electrical engineers, with computer scientists, with mathematicians, and we're trying to find interesting problems here. And one of the things we're learning is that the quantum algorithms that have been developed to solve sort of optimization problems like this often have deficiencies for solving the types of engineering problems that occur in practice, and we're trying to remedy some of those. So I'll tell you about that. And I'm actually going to tell you about it in the opposite order. So I'm going to start by telling you about some of the digital quantum algorithms we have for solving optimization problems, and then I'll tell you about how we're thinking about sort of analog quantum simulation to simulate materials in chemistry, and then how to combine them. Okay, so is this kind of broad overview of what I'm going to talk about clear? Does anyone have questions here? Cool. Okay, I see a thumbs up, so I'll give 5 more seconds and then move on. All right, good. So optimization problems, why do we care about them? Well, I think I told you why we care about them, but let me tell you a little bit of how we're going to solve them. And actually, I'm pretty light on the details here, so if you are curious, just stop me. I think we have plenty of time to discuss it. So the approach we're going to take to solving these optimization problems is the variational quantum algorithms that I mentioned before. And an example of a variational quantum algorithm is this QAOA or QAOA, or I forget actually what the letters stand for. It's been abstracted beyond its original approach. I think my favorite acronym for it is Quantum Alternating Operator Ansatz. I think the original was something else. It was originally stood for Quantum Approximation Optimization Algorithm or something. Anyway, but the point is there's some example of this variational quantum algorithm. And what you do is you start with a bunch of qubits over here on the left. You execute some initializing unitary. Very often this is a very simple gate. You know, maybe you just rotate all the spins by some amount independently. And then you alternate two types of evolutions over and over again. So I apply evolution 1, evolution 2, evolution 1, evolution 2. And you just go back and forth, back and forth, and back and forth. And at the end, you measure. And the only thing that changes from each application to each application of this pair of operations is the time you apply it for. So there's this alpha 1 parameter. So basically it's saying I apply this first operation for a time alpha 1, or if you like, it's a parameterized unitary, if that seems like a more comfortable way of talking about it. It's a unitary that's parameterized by some alpha 1 that you can imagine going between 0 and 1. And then at the next step, you do the same thing for this second type of evolution. So you see there's a z here, and then an x, and then a z, and then an x. That's just going back and forth between these two types of evolutions. And we have different angles, alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3. And the idea is that you're going to run your circuit, you're going to measure your answers, and now you can see how good are your answers to the problem. There's some cost function you compute that, given a solution, tells you whether it's a solution or not, or tells you how far it is from a solution. And so you go through and you do your measurements, you see how well it's doing, and then you can feed those results, you make a table of that. You tell a classical computer what angles you picked and what result you got, and a classical computer tells you how to change these angles to try to get a better answer. So you can imagine that this is a hybrid classical quantum algorithm, where the quantum algorithm is used to run this circuit, and then the quantum algorithm is used the quantum hardware is used to run this quantum algorithm, this circuit, and then the classical algorithm takes the results of that, just viewing it as a black box, and optimizes the alpha 1 and beta 1 according to standard optimization techniques. Okay. And there is a world of interesting results in how to actually do that classical optimization. But for the point of this talk, and we're working on a lot of this, but for the point of this talk, I'm just going to assume that we can do this classical optimization. You should certainly not always assume that that's possible. We know many, many obstacles to that being possible. So, but that's a talk for a separate day. So there's been a lot of interesting work about if you pick the right operations, hz and hx, that we apply over and over again in this back and forth pattern, then you can solve interesting combinatorial optimization problems. What I really want to tell you a story about here is a little bit how those fail, how we can fix them, but also very much an experimental story. And so the experiments on this type of algorithm, it turns out they rarely get past this point. I hope you can see my laser pointer. Maybe somebody gives me a thumb up if you can see my laser pointer. Yeah, okay, good. So you can run the circuit out to here, meaning one round of QAOA. One round means one alternating pair of the Z and X. But the quantum hardware would decohere before you could even do 2 or 3 rounds. And moreover, that was with the simplest choices of these sort of operations Z and X. With more complicated choices, you couldn't even do 1 round. So I want to show you some experimental advances and where we're at now, because we're starting to push that frontier, and that's really important for solving the types of problems I'm interested in. Okay, so here are the experimental results. Just starting with sort of a traditional algorithm, one of the original sort of QAOA type algorithms as it was introduced, where we apply what's called a transverse field mixer, and I'm happy to tell you what that is. But it's if you look at this panel A, this top left panel, it's this right set of gates, the UM beta. You just independently apply a X rotation to the 3 qubits I'm showing here, or to all your qubits. So when I say transverse mixer, that's all that means. It just means you independently rotate all of the qubits around some axis. And then, so that's, remember we have these 2 operations. That's not only our initializer, that's also one of those 2 operations. The other operation is in the rest of this quantum circuit, and that's what actually encodes the problem we're solving. I won't talk through how you can get this, but it's straightforward to get these types of circuits. I'm using an abbreviated notation here because I don't have room to draw out the full circuits with conventional notation, but the The little dots, whether it's a triangle or a square, are just rotations around some axis. The two squares connected by a vertical line are an XX gate, which can be built from a C0 gate and single qubit gates. And then Hadamard gates are these little vertical lines. So I suspect you've seen all these gates in what you've been playing with. And so this is gives you an idea of the circuit schematic of what we run, or what our collaborators run. And the problem that's being encoded in this top left panel is what's called an edge cover problem. So in an edge cover problem, you have a graph. Here it's a triangle graph. And what you want to know is I can lay down an edge. So either I can put an edge down or not on each of the three possibilities for this triangle. And what I want to know is each node in this graph attached to at least one edge? If it is, then we say it has an edge cover. So for example, if I had no edges, I would clearly not have an edge cover. Each node would not be connected to an edge. If I just laid down one edge, say this bottom piece, then this would still not be an edge cover because the top node would be disconnected. It would not have an edge attached to it. But as long as I lay down two edges on this triangle, then I have an edge cover because each node in that graph is going to be attached to an edge. So for example, if red means there's no link and black means yes, there is a link, then the configuration I've drawn is an edge cover here. And so what we'd like is out of all the possible edge configurations, and think for a second, how many edge configurations do we have here? There are 8 because I have 2 choices for this edge, 2 for this edge, 2 for this edge. So out of these 8 possible configurations, I would like to know how many of them are edge covers. Okay, and so I think the number is 4, but we can come back to that later. So I can either have, I can either have all 3 edges, or I can have any 2 of the 3 edges, and there are 3 possibilities for that. So those are the 4 solutions. And what we're plotting here on this vertical axis, this is the probability that you get a solution. Doesn't mean that you find all 4 solutions. It means that the output of your quantum circuit is one of the 4 solutions. That's the vertical axis. And the horizontal axis is the number of rounds of the QAOA. So we have this UP and this UM. It's what I was calling Z and X in the previous slide. And we're just going back and forth between them. And P is telling us how many times do I go back and forth, the number of rounds. And you see that if I do 2 rounds, I get a higher probability of finding the ground state than 1 round. Okay, and this is a general feature. The more rounds you do with these variational quantum algorithms, the better answers you get, because you get what, however close to the solution you got before, then the next round helps you tweak and get closer. Then the next round helps you tweak and get closer. So you see we're getting very high solution probabilities for this admittedly extremely simple problem that you could solve by hand on paper or maybe in your head, but still it's nice to see. And interestingly, maybe with 1 or 2 other exceptions, never has this been demonstrated in hardware that you can get an improvement going from p equal 1 to p equal 2. So even though these variational quantum algorithms, the idea is always you make them deeper and you get better, this was only demonstrated recently by Google. No one else has ever achieved this. But the results I'm showing you here in these graphs are all experimental results from our collaborator Norbert Linke at the University of Maryland. So we see we're getting a clear improvement here. And the reason is simply because quantum hardware is getting much better than it used to be, and we're able to solve these new types of problems. And then the rest of these graphs are just to show it's not just the triangle graph. We've done this on the square graph. Actually, the bottom left is a different problem. It's not edge covers. It's something called max cut. And then there's this, we call it a paw graph, because if you look at it the right way, it kind of looks like an animal, like a cat paw or something like this. And this paw graph, we've also run it on. You can see it requires by far the deepest circuit and also the most qubits. This is 1, 2, 3, 4 qubits. We can do bigger graphs, but at some point, you just don't get very good results. The decoherence is much more important than the qubit number for us. But you see in all of these cases, we get increases going from p equal 1 to p equal 2, from p equal 1 to p equal 2, from p equal to 1 to 2 to 3 even, and then maybe some improvements here. Okay, so that was great, but it turns out there's a fundamental difficulty with using these results for the types of applications we're interested in. And remember I told you we wanted to do things like determine the reliability of a power grid. So that's actually pretty closely connected to this edge cover problem. But the issue is we don't just want to find a reliable solution. We know a reliable solution to the power grid, which is you just make sure that all of your power links are working, all your power lines are working. Instead, what we want to know is what is the probability of getting a solution. So we need to be able to find out how many solutions are there, find all the solutions. And there are many other important engineering problems where you want to find all the solutions. And it's a well-known fact. In fact, other speakers, I think Helmut Kotzgraber is going to talk about, or may talk about this, or has done work on this. It's a well-known problem that you do not sample all the solutions equally. And in fact, they're very, very unevenly sampled. In fact, you can totally miss solutions where you have essentially zero probability. So this traditional algorithm doesn't work very well. So we worked theoretically, we showed in this paper I'm referencing here, that there is an algorithm to sample all the solutions equally. And I think it's, once you think about the problem a little bit, it's not a particularly surprising algorithm, but it's nevertheless important to work out, and others have since rediscovered this. But the downside of this algorithm is that on current hardware, it requires much more complicated gates, in particular what I'm calling mixer. So remember this transverse mixer, this it's just this very simple thing in the plots I have on the left. You just independently rotate all the qubits. To do uniform sampling, you have to make that a much more complicated circuit, a circuit that's maybe even more complicated than the other things I'm drawing here. And so on existing hardware previously, that would really not run well. But what I want to show you is results from Norbert's group again, showing that we are now reaching a stage where such mixers can be used to get great results. And so on these left panels, so the left column here is 1 round of QAOA. The right is 2 rounds of QAOA. And the different rows are just different graphs. So the top are the triangle graph, the paw graph, and the square graph. So if you want, let's just start by focusing on this top left graph. This is showing 1 round of QAOA to solve edge covers on the triangle graph. We said there were 4 solutions, which is what I'm showing the probabilities of here. And if you just run the traditional thing, that's this light blue, what I call the transverse mixer, you see that you do not get equal solution probabilities. This solution with all 3 edges covered is a much higher probability than the other 3. But there's this new type of mixer that we introduced, the one I said I gave the citation for in the previous slide. That's implemented in these purple results. And you see the purple results now give an almost uniform solution probability. And it doesn't look like it might be all that helpful for 1 round of QAOA. But if you look at 2 rounds of QAOA, you see the traditional mixer, this blue thing, is really, really unbalanced. There's a huge weight, 95% of the weight or 90% of the weight is all in this one solution. And there's almost no weight in these other solutions. So if you try to find all the solutions with that algorithm, you're in trouble. You'll very rarely see these other 3 solutions. But you see with the new mixer we've introduced, you get pretty uniform results. And again, on previous experiments, this just never would have been possible. The decoherence would have been too bad, but Norbert Linke's very nice hardware has let us get good results. And the same thing is true for all these different graphs. We've used not only Norbert's hardware for this, but we've ran a variety of things with IBM hardware. So this is plot on the right is sort of summarizing some of that. The horizontal axis here is the probability of finding a solution, any solution, of being in the solution space. And the vertical axis is what we call fairness. It's a measure of how uniform we are sampling things. And in both cases, higher is better. So the best results would be in the upper right-hand corner of this plot. And so the results I showed you from on the left from Norbert Linke's hardware, that's these squares here. And all the IBM hardware is these kind of blue triangles and circles. These are different machines and different optimization levels. And overall, I think it's clear that that Norbert's hardware is somewhat ahead of what the IBM machines are giving us. These are the sort of machines that are available through the Quantum Researchers Program. So, but nevertheless, even with the machines at IBM, they're still giving, quite reasonable results with solution probabilities in excess of 50% and 100, whatever that may. I haven't defined how we actually calculate this fairness score, but 100 is a pretty good score. So there's now a lot of hardware that's becoming capable of running this, and we have a agreement with IonQ where we're looking at running some related things and also some related things on Honeywell. So we should have a much better global picture. But anyways, these sorts of algorithms are really opening up to us now. So really, that's on the digital front what I wanted to tell you about. Then I'll tell you about the analog and how to combine these. And I think the conclusions are right here. More tailored mixers are possible. These are necessary to solve the types of engineering problems where you're trying to find all solutions. And so it's an exciting time to start playing with this. So before I move on to the analog stuff, does anyone have questions about this? I'm happy to answer anything.
So the mixer in the updated version incorporates Grover's algorithm?
Yeah, that's exactly right. So you picked up on this. So I said I wanted to fairly sample. And the way we do it, so traditionally we have this Z evolution quantum operation, that encodes the problem. So that encodes like the triangle graph and what the edge covers we're trying to solve. Whereas the X operator traditionally was this transverse mixer where you just independently rotate spins or qubits. And so what we've changed is this mixer. And instead of applying the transverse mixer, we apply what we call a Grover mixer. And that's exactly the operation in Grover's algorithm that, not the Oracle, but the other operation. So the Grover diffusion operator is, I think, what it's typically called, which sort of just takes you from one state to all the other states. And the reason it works is because it has a symmetry, because this diffusion operator is sort of symmetric under permutations of all the states. Well, then your final answer should be symmetric under all permutations, except to the extent that this other operation breaks that symmetry. And this other operation doesn't break the symmetry for solutions, but only between solutions and non-solutions. Mm-hmm.
Yeah, cool.
And I think this is, so it's hard to actually give rigorous performance guarantees, right? I haven't actually told you anything about the scaling of these algorithms. You know, for all you know, maybe this runs slower than classical algorithms. But I would say there's one case where we have rigorous results, and that's when you make a particular choice for the problem in for Z, and then this reduces to Grover's algorithm. And in that case, there's a provable quadratic speedup. And then I have numerical results for things like the edge covers, which are shown in this paper that I cited here, that actually suggest there's some sort of polynomial speedup for other problems and not just Grover. And the dream, of course, is that there's an exponential speedup hiding somewhere, but we haven't found it yet. But maybe even a polynomial speedup can be interesting someday.
So edge cover can be solved in polynomial time, right?
Yeah, edge covers. So edge covers is a little tricky. If you actually want to count edge covers, it turns out exact counting, I believe, is a combinatorially hard problem. I don't know if it's MP, but it's not a efficiently solvable problem. But if you want just an approximate counting, there is what's known as a FP-TOS algorithm, I think is the terminology. So if anyways, basically a polynomial algorithm for finding a approximation to the number of solutions. This is unfortunately something which we only realized after we started running all of this, even though it's kind of obvious. I don't know what we were thinking. So the thing I would suggest is that I don't think that any of the quantum results really depend on the specific problem used, that the kind of speedups you're getting probably persist even if you're not doing the edge cover problem. And we do have some numerical results that indicate that, but it's a very good point that in principle there is a polynomial efficient approximation algorithm for doing edge covers. Yeah. I would be shocked if the quantum algorithm is exploiting any of that structure, though. It would be remarkable if it was. Yeah, any other questions?
I had a question.
Mm-hmm.
So when you were talking about the variational quantum algorithms and you talked about the to minimize the cost of that algorithm, you would send it over to a classical computer. But would it be possible to just use a quantum optimization algorithm to optimize the experiment instead of passing it to a classical computer?
So that's a really interesting question. And the answer in principle is, so there's a sort of trivial in principle yes answer to this, which is that a quantum computer can run any classical algorithm. The issue is that quantum computers, for doing things you can do on a classical computer, are much, much, much less advanced, right? So if I just want to do arithmetic or something, I can do that a billion times a second on my laptop, but doing that on a quantum computer, good luck, even adding two numbers at once. You'll decohere first. And so although you could in principle do that optimization via quantum circuit itself, at the moment you get a big win from being able to outsource the classically easy stuff to a good classical processor. Okay, and so now whether that will always be true, I don't know, but I think for the foreseeable future, there are a lot of things that it's just very difficult to do in the quantum circuit itself. And that's one of the reasons people like these variational quantum algorithms, because it lets the quantum computer focus on the things where it really has a unique advantage and maybe outsources some of the stuff where it doesn't have a unique advantage to the classical system. But the right mix of this kind of quantum classical separation is certainly not predetermined and is a evolving and interesting problem in its own right. Cool. All right, so feel free to ask more questions if you have them, but otherwise I will move on to the kind of second part of my talk. So the second part of my talk is, rather than using all these digital quantum algorithms that I've told you about, what if we used analog quantum systems? So if I want to understand this high temperature superconductor, rather than programming a quantum computer to try to sort of mimic what it's doing or solve for the ground state, what if I just built something that kind of looks like a high temperature superconductor and lets me explore its properties and maybe learn things? So I'll tell you, a little bit about this. So why do we need these quantum computers to solve the materials in the first place? There is a theory of everything, almost everything, a theory of almost everything. Certainly a theory that governs everything in the room sitting around you. And even if you had a high temperature superconductor in the room, we believe it governs that. And that theory is simply the Schrödinger equation, the quantum mechanical equation governing electrons and nuclei. And if you could solve that equation, which is written out in full on the screen, then that presumably tells us everything we would want to know about these materials and chemical reactions and everything. The unfortunate thing is that we can't actually solve this. And I think this is really well encapsulated by a quote from Feynman, who says, today we cannot see whether Schrödinger's equation contains frogs, musical composers, or morality, or whether it does not. And I think it's hard in one sentence to say it, more profoundly than this, that we have the equations, but we cannot solve the equations. And so that's, at least on a classical computer. And so that's why we have to bring alternative techniques into understanding these materials. And so, in a cartoon, does the Schrödinger equation lead to Beethoven? I think that's Beethoven. Mozart. Anyways, I'm now embarrassing myself, but someone else will tell me. And we can't just solve this. The reason we can't just solve it, it's not just that there are a lot of electrons. There's like a mole of electrons, which is 10 to the 23 electrons or something in a tiny chunk of material. But it's more than that. It's that the computational power required to simulate these systems grows exponentially with the number of components. So the computational time to, say, even calculate the dynamics or the ground state is going to go like 2 to the number of electrons or 10 to the number of electrons, but really bad. You'd like a polynomial thing. And so as an example of just how hard this can be, take something simple like a chromium dimer. So you just take 2 chromium atoms, they bind to each other to make a diatomic molecule, and it turns out nobody knows how to solve that problem. 2 atoms. So this is a far cry from, a biological enzyme or a complicated material with hundreds of different types of, hundreds of atoms in some complicated arrangement. This is really a simple looking problem that turns out nobody knows how to solve it, at least in a controlled way. And as another example, there is this problem of high temperature superconductors. So on the top right, I'm giving a phase diagram just showing the different phases of matter that occur in a high temperature superconductor as you change the temperature and something we call the doping, which is just the number of electrons in the material. And you see there's a superconductor here, and there's also a bunch of other stuff, and we don't understand any of it. And so physicists for 30, 40 years have tried to simplify and make models of this to understand. And the simplest model is just that you have a square graph, and electrons can move around on this square graph, and the electrons can either be red or blue. They can be spin up or spin down. There are two possible choices for what the state of the electrons is. And if they're on the same site, there's some interaction energy. So, and it turns out even this simple model, nobody knows what it does because of this exponential scaling of the problem with system size. Okay, and so this is what you'd like to use a quantum computer to solve. And people are working on doing this with digital models of quantum computing. We're even working on doing this with digital models of quantum computing using variational algorithms like I told you about in the first half. But for the rest of the talk, I actually want to focus on an alternative approach and how it may dovetail into the digital approach, which I think is very interesting. So the solution is you fight quantum with quantum. Rather than programming something, you actually just build something. So if you have a high temperature superconductor you'd like to understand, you build some experimental system that looks just like it or behaves just like it, and that you can mathematically show will behave in the same way. And in practice, it looks a little more complicated than my cartoon. It's not the LHC, but it's a room full of electronics and lasers and things. But nevertheless, you can build a system to mimic a high temperature superconductor in a sort of tabletop experiment like this. And here are some experimental snapshots. This is actual experimental data where you can see the experimentalists can see and control every single atom that they're using to mimic the real material. So here there's a lattice that the experimentalists have built. There are atoms that live in that lattice and can move around. And this is exactly the same mathematical model as I described to you before, the mathematical model that people want to use to understand superconductors. And so they've built the analog of this using atoms cooled down to nanokelvin scale temperatures, very, very cold, coldest systems in the universe. And the great reason to go so cold is because you can image and control all of these atoms just like you're seeing. Or earlier, I showed that picture of the Eiffel Tower, and you can build that picture of the Eiffel Tower out of atoms and control it all. So now I'm showing it again. So there it is. And so there's been a lot of progress understanding what do these high temperature superconductors actually do with this approach. I'm just putting a bunch of little nice pictures of what people have done in the past. They've seen how the electrons start talking to each other and the types of correlations that build up. And we've done some research on this. I'm just going to spend one slide mentioning this. If you generalize this Hubbard model, there are reasons to want to do this to understand materials, to not just have red and blue, but to have red and blue and green, have 3 or 4 or 5 different flavors. Lots of different ordering patterns have been predicted, and exotic topological states of matter that physicists care a lot about have been predicted. But again, nobody knows what's going to happen. So with experimental collaborators, Yoshiro Takahashi in Japan, they've went and actually measured what happens in these systems. And just given the time and things, I'm not going to tell you really what happens. I just want to make the point that they've realized 100,000 particles in this system. They're interacting quantum particles, and they have a lot of behavior that makes it very difficult to simulate using classical systems. So using state-of-the-art stuff, here are some 1D results. There's data for a couple configurations. Again, not going to tell you what's going on. The solid line is the theory that we did. The open dots are the experiments. It agrees reasonably well. But the real reason I'm showing you this without telling you what it is because I want to show this red data. So the red data is a simulation of a 3-dimensional material, of these 3-dimensional materials of high temperature superconductors. The red dashed line are the theory results from a very sophisticated theory known as quantum Monte Carlo. And this requires thousands of CPU hours, tens of thousands of CPU hours to get this red curve. And the simulations get harder and harder as you go to the left on this graph. Going left corresponds to lower entropy or lower temperature. And you see our classical techniques fail far, far before the simulation or before the experiments. And so in this sense, the experiments are serving as quantum simulators. They're simulating physics that is beyond the reach of classical computers to simulate. And this is unlike, in terms of the scale, this is very different than the digital approach we discussed in the first half of the talk. In the first half of the talk, we had some really nice experimental results, but they're all well within the regime of what can be solved on a classical computer. You can go solve the edge cover problem by hand for all the results we showed. In contrast, these analog experiments are already far beyond what's possible to simulate classically. And so that makes them very appealing. Of course, the analog experiments have a big drawback. that the digital experiments don't. And that is that they are not fully universal. They cannot implement any quantum algorithm. They can only do very specialized tasks. And I'll come back to that. Before I do that, I did just want to advertise that actually these experimental results are the coldest system in nature made of fermions. So there are two types of particles in nature, bosons and fermions. Electrons are fermions. And this is the coldest system actually in the universe as far as we know, unless there's an alien civilization out there running experiments on ultra cold gases. This is about a 1 nanokelvin fermionic system. And that's by far the coldest in nature. Okay, so now we can go back to this idea. So the summary here is just that analog quantum simulation is already solving problems with hundreds of thousands of particles and well beyond the capability of any classical computer as far as we can tell. So this red line I had mentioned to you, just extending it, 5% to the left would require a huge increase in computational resources. Okay, so that's more or less the second part of my talk, and then I'm just going to have sort of one slide combining these two parts. But I want to pause. Are there questions on the second part about this idea of using analog quantum simulation to solve problems? Everyone got quiet since I'm not showing circuits anymore. Okay, so I'll talk for a little bit, and feel free to stop me. I think the key thing here is this sounds very desirable. We certainly don't have systems of quantum coherent systems of hundreds of thousands of programmable qubits, but we do have hundreds of thousands of interacting quantum particles that are apparently pretty coherent, at least as far as we can tell. They're reproducing the types of physics that you'd like to see. So the final thing I wanted to mention is simply, can we combine these capabilities? And this is where we come back to the variational quantum algorithm. So what if instead of applying, say, we had this Grover operator that we talked about, and we had something that encodes our problems, but I don't have to use the types of digital circuits that I showed you before. I could use for example, I could use this analog quantum system, this Hubbard model, what I call the Hubbard model. I could just implement the time evolution of the Hubbard model. Or in other words, in this custom-built system that people have made to simulate it, you just let the atom sit there for some amount of time. And the amount of time is now your variational parameter. And I could do various things like this. And what this would do is it would let me harness the hundreds of thousands of coherent particles. But now, instead of being tied to only simulate the specific model that I built, the Hubbard model, it would increase the flexibility of the sorts of algorithms I could run. I could simulate that model, I could simulate other models, I could maybe go back and simulate, do calculations for combinatorial optimization like we talked about. And so I'm calling these hybrid algorithms, really hybridizing the sort of analog evolution of these Hubbard or other types of models and the digital type programmability of being able to apply a certain prescribed set of gates and optimize that set of gates. So this is really everything I wanted to say. So already analog quantum simulation is far beyond the reach of classical simulation. Digital quantum computation, I think, is entering this really interesting regime with these variational quantum algorithms where we saw we could do deeper circuits so that multiple rounds of variational quantum algorithms actually improved round by round, but also more sophisticated mixers, more sophisticated in each round about how we find solutions. And the example I gave was how to fairly find all the solutions. And we saw that both of those are becoming capabilities. And at the end, I'm trying to point towards the idea that we can combine the large number of qubits and inherently parallel gates over 100,000 particles with digital programmability and scalability using these variational quantum algorithms. So that's everything. Thanks for listening, and I'll hang around and chat with you until your next talk. Thanks, everybody.
Thank you. So what's the strategy for this plus sign here? Digital programmability and scalability.
That's a great question, and that is exactly the sort of research problem that we're working on here. So let me give you a concrete example of, I actually have some results I could show you, but I just don't have them on the slides. So what we've particularly taken is a set of evolutions where the pair of operations that we pick, one pair is we have a bunch of qubits, but rather than applying a bunch of C-naughts and Hadamards and things like this, instead what we apply is sort of interaction. Actually, let me just to show you a picture. Let me go back. Where did I have it? Yeah. Okay, so you see this picture of the ion trap at the top. Here, there's a qubit on each of those ions, and there's an interaction. Maybe I can draw, actually. Let me see if I can do that. We're definitely pushing my tech savvy here, but I think I can maybe do it. So there's an interaction between all of these qubits, okay? Even if they're far apart or close, the interaction strength depends on the distance, but if you just let them sit there, they're all interacting with each other. You can see the little red lines that I drew. Is that good?
Yep.
Okay, good. So they're all interacting with each other. And so what you can choose as one of your operations is just let these ions interact with their naturally occurring interactions, which are somewhat tunable, but also not fully tunable. That's going to be one of your operations. And then your other operation is going to be just single qubit rotations, which are very possible in this architecture. And so this is an excellent example of the type of scheme I'm thinking of, because rather than having to do all these interactions between the ions by decomposing it into a bunch of successive C-naught gates, you're in parallel applying all of these gates at once in some sense. And you're applying them in a way that really mimics a lot of the problems that you'd like to solve. So especially if you're doing quantum simulation, if you're trying to simulate a real materials have some interactions between spins and maybe these decay, and it might not be the exact same interactions that are in your trap, but at least it's qualitatively kind of similar. And so by using that inherent parallel nature, the sort of nature of the interactions being tailored to the problem you're trying to solve, you can potentially get big speed ups this way. And so you can also do other things. So, for example, if you have a continuous variable, this is pretty awkward to encode in qubits, right? So a floating point number takes a lot of qubits to describe, right? If I just have a value between 0 and 1 that varies continuously, encoding that to qubits, I have to use a lot of bits, and then I have discretization and all this. And if I just want to do something simple, like multiply two numbers, or as a physicist, maybe solve a harmonic oscillator just for one particle, I would have to encode the position of that oscillator using lots and lots of qubits. And I'd have to do arithmetic. And the issue is that a quantum computer may not even be able to do simple multiplication of two numbers. It may decohere before the result finishes. Whereas if I want to do this multiplication sort of using this type of hardware, there are actually continuous degrees of freedom in the motion, and I can very easily solve, say, the dynamics of a harmonic oscillator or do certain operations with continuous degrees of freedom in that system. And so you could take advantage of that. And similarly, fermions, which were really crucial for all of those materials, those are really tough to encode in qubits. There's a big overhead for doing that, factors of, I'm going to say 1,000, although it depends on what you're counting and what algorithm you're using. That sort of, if you work directly with fermions instead of qubits, so doing fermionic operations, you can circumvent that. And so you inherently get rid of that overhead. So that's why I'm hopeful that these could be interesting. They have challenges of their own, really quantifying these systems have not had their coherences as well quantified as other systems, and maybe it's not as coherent, so there will be trade-offs, but it's certainly worth exploring, I think so.
I think we are just about out of time for questions until I think Andrew and Worley will do our next talk. But thank you so much, Kaden, for coming to this talk about your research. I think it's really great for students to hear some of the more upper level research going on that they can get opportunities for if they do choose to pursue a PhD or master's within the field.
Yeah, it's been great talking to y'all, and feel free to get in touch later. So see y'all.
Thank you.
Thank you so much. I'm also not going to end the Zoom since our next two speakers are going to be doing their talks at around 2. So if you guys want to stick around for the next two guest speakers,